Hey, let's now talk about dynamic memory allocation. If we declare an array in this way, as I did here in this program, int x20, then it's typically a compile time allocation. That means while compiling this source code, the compiler is going to write the memory allocation instruction for the operating system. And during the execution period, operating system exactly follows the instruction written by the compiler in order to allocate the memory. You can compile the program today, but you can run the program anytime later on. When you run the program, obviously at that point of time the memory gets allocated, but it's exactly according to the instructions written by the compiler. Now compiler knows that int type takes 4 bytes, so for an int array of size 20 it's going to be 80 bytes. So compiler writes instructions for 80 bytes of allocation to the operating system, or for the operating system, and operating system does exactly what compiler writes into the object file. So this is typically called the compile time allocation. The main problem with the compile time allocation is that we cannot change the allocation during the execution period, but often it may require to change the allocation according to the need of the data size. Now when we are writing the program, it's sometimes impossible to imagine that how much memory is going to be required during the execution period. Let us imagine this situation. I need to develop a payroll system for a company, and the number of employees of the company may vary. It's not fixed. So I need to declare an array in my system, in my program, to hold the salary information. Now, what's the size of the array going to be? If I go on and declare the array with 100 elements, then I am making the provision for 100 employees. But if there are 150 employees in practice, then there's going to be a shortage. Otherwise, if there are 50 employees, then and I'm declaring 100 elements array, then it's going to be a wastage. So with the compile time allocation, there are chances of frequent shortage and wastage of memory. And it's impossible to guess exactly what's going to be the requirement in runtime. We write the program today and the runtime is in future, so we cannot guess how many memory is going to be required according to the need of the runtime situation. So it's better to actually allocate the memory in runtime in some situation, in most of the situation. That's practical, and it's going to be impractical if we just go and guess blindly and allocate the memory. That will generate frequent shortage and wastage of memory. In runtime allocation, compiler never generates any instruction for memory allocation. Rather, we call some utility function, and that function does the needful to allocate memory during the execution period. So runtime allocation means the memory is acquired during the execution period, and the compiler never writes any instructions for that. And runtime allocation is exactly according to the discretion of the programmer. We can allocate exactly the memory that we need, and as long as we the programmer want, we can retain the memory, and when the job is done we can free the memory back to the free store. So the memory management is again in our hand. We can allocate and deallocate according to our need. Okay, so there are 3 functions in C. There are 3 library functions in C programming. They're given in the stdlib.h. We need to include that, and the functions are malloc, calloc, and realloc. So we can use these 3 functions for allocating dynamic memory, and the dynamic memory is actually allocated in the heap area. I have already introduced what heap is and what stack is. If you are not familiar with that, you can just get back to the first tutorial of this section. So dynamic memory is always allocated in the heap area. Now we can use the malloc function, and for dynamic memory allocation you obviously need a pointer in order to store the base address. So I'm declaring an integer pointer. Now the malloc function, if called, it requires the total number of bytes that it needs to allocate as parameter. That means we need to supply the number of bytes that the malloc is going to allocate during the runtime as parameter to the malloc function. So if I'm calling malloc passing 100, then the malloc is going to allocate 100 bytes in the heap, and it's going to return the base address as void pointer. Because I'm asking the malloc, or we are asking the malloc to allocate the memory, malloc will allocate the memory, but malloc doesn't aware of the fact that what we are going to keep in the memory. We can keep 100 characters in 100 bytes, we can keep 25 integers, and we can keep some 12 double values. It's up to us that what we are going to keep in that location. So malloc is not aware of the fact that what's the type of the address. It only allocates the memory which it is asked for, and then it returns the base address of that allocated space as void pointer. So we need to keep that in some pointer variable. Now my intention is to use that space allocated by malloc to store the integer. So I need to convert it or cast it explicitly to integer pointer, and then I'm keeping it to the pointer variable p. So here's the block diagram. It will just elaborate the thing in much easier way. So we are asking malloc to allocate 100 bytes. So malloc is going to allocate 100 bytes in the primary memory. So this is the area, and say it has started the allocation from 2000th byte of the memory. Now this 100 bytes can be used for keeping 100 characters. If that is so, then this base address has to be converted to character pointer. Otherwise, if we use this 100 bytes for keeping integers, then for each 4 bytes we are going to keep one integer. So this initial address is going to be of type integer pointer. But malloc is not aware of the fact. Malloc's duty is to allocate the memory. So malloc does that and returns the base address as void pointer, and we are converting it by explicit typecasting to our appropriate need, and we are assigning that to p. So since p is the integer pointer, so it is receiving that 2000 and p is pointing to this location. Now star p means first 4 byte. Now if I add 1 with p, it will actually jump to the next integer location by adding 4 with itself. So I can just hover over this area and get each 4 bytes content as integer. That's how we allocate using the malloc, but it's possible that we may not know the exact amount of memory that we need in runtime. That may depend and vary with the different execution. So say we need to write a program that is going to input some integer number. So first of all, and we are not sure how many integers the program is going to process, so I'm just asking the user for the numbers that the user is supposed to input, and I'm keeping it in a variable n. So this n is going to be supplied during the runtime, and we can as well take that value for n from a text file as well, that I will be showing you later on in the file handling section. Now n is the number of values that the program is supposed to process, and say these are the integer values. So I can just go on and write in this way, and that's going to be more platform independent, because integer may have different size in different platforms according to the different compiler specifications. So what I am doing, I am using the size of operator in order to get the size of integer under the platform in which this program is going to execute. So possibly it's going to get us 4 in most of the cases. So 4 multiplied with the number of integers that the program is supposed to process. Say here the user has given 100, so 4 multiplied with 100 is 400. So we are passing 400 to the malloc function, and malloc is in that case is going to allocate 400 bytes in primary memory. Please remember that malloc, calloc, realloc, all these dynamic memory allocation, all these functions which are doing dynamic memory allocation, allocates memory contiguously. So the memory will be allocated. Now it's not guaranteed that the memory is going to be allocated every time. It may happen that the runtime environment, the operating system may fail to find the contiguous space that we are requesting for due to some adverse situation. In such cases, if the malloc fails to allocate the memory, it returns null to the caller. That means if malloc returns a null, then we should understand that the memory allocation failed and we should exit from the program or the function. So we should have a runtime exceptional checking here, that if p is null, then I'm just printing a message. It could be to a log file, that would be appropriate. So unable to allocate memory, exiting the program, and we are just returning, or we can use the exit function in order to terminate the program passing 1. 1 indicates that there are some bad situation in the program. And if we exit passing 1, then the operating system or the calling environment understands that there is an exceptional exit, it's not a normal exit. If the 0 is passed to exit, then the calling environment will understand that it's a normal exit. Okay, so we should check it always when we are actually doing the runtime allocation. And now we can use the allocated space pointed by P for keeping values. So I'm just declaring an integer variable and writing a for loop to iterate over the allocated space that we did dynamically, and just taking some value there. And I'm using pointer notation. P plus I means the address of the ith element itself. P is the base address, and everything is just like array. We could have used the array notation as well, so this is also possible, no problem with that. So I'm using the pointer notation directly. That means P plus I is the ith element, and then I'm just printing the content. The specialty of this program is that we have allocated the memory exactly according to the need. That means on the input value n. So this is going to be supplied in runtime, and according to that the memory is going to be allocated. So here I'm running this. You have seen that I have used the pointer notation again here. So it is asking for the number of integers. I am giving 5. So 20 bytes will be allocated. Now I'm just supplying some numbers here, and they are assigned to that dynamically allocated space, and you can see that is printing back from there. And one more thing that I would like to mention here that's important: whenever we are acquiring memory by using dynamic memory allocation technique, then it's our responsibility to deallocate the memory as well when the job is done. For that, there is a function called free function, and we can use that free function in order to return the allocated memory back to the free store of memory. So I can call this free function and pass the pointer which is pointing to this dynamically allocated location, and this is going to deallocate the memory as soon as the function is, as soon as we call this. Okay, so this is a better approach. Otherwise there will be a chance of memory leak. The unused memory could increase in your system, and that will lead to an adverse situation, and it could go to such extent that you may not be able to acquire memory dynamically anymore if unused spaces increases drastically. So this is how we can use the malloc function in order to allocate memory dynamically. Hope that you understand. And in the next tutorial I'm going to talk about the calloc function. That's also can be used to allocate memory dynamically. Thank you very much.